Hi everyone, and welcome to our IBM Kubernetes intro session. Up front, for those of you that have attended the Kubernetes from Zero to Hero sessions in May and June last year, the next session will be announced very soon. For those of you who didn't attend them, this session could give you an overview of the IBM Cloud Kubernetes services, so basically a refresher from microservices to Kubernetes, or a possibility to attend the follow-up sessions of the Kubernetes from Zero to Hero session. Niklas Hurd, our cloud guru, will now take over and lead the presentation, the intro.
Yes, here we go. Can you see my screen, Christina?
Yes, very well.
Okay, perfect. So, Hi guys, thank you for joining. We have 1 hour in front of us to do a short refresher about microservices and containerization and Kubernetes. I've seen there are some familiar faces in the attendee list. So it will basically be what we already covered back in May. So there has been a little mix-up with the invite. So this is really the refresher, and the Kubernetes advanced concepts will be announced very soon. We have to check that with Yuri when we can fit that into the schedule. So for those who already followed that and don't want this refresher, you can disconnect now, or you can stay in and we can discuss a little bit. Okay, good. For those who don't know me, my name is Niklas Hurd. I started programming like over 35 years ago at age 11 with a Commodore computer back then. So I grew up in Bern, went to the École Polytechnique Fédérale de Lausanne, in computer science, worked at different positions, and I've been with IBM now for 10 years. In different roles, and for some time now I'm what we call a DevOps/cloud architect, basically helping our customers implement and transform their IT infrastructure. Now, very recently, just before we started the last series, I'm part of the MVP team, so I'm doing minimal viable products with customers together in co-creation. So that's about me. Today, so it will be pretty short, 1 hour. We'll be talking a little bit about microservices, containers, and Kubernetes. So it's really just a refresher. If you want to go more into detail and do the training, you have everything here in the documentation. We will post that as well in the meetup invite, so you can get that, and you will get at the end also the link to the video recordings that we did of the 6 installments that we did. So there were about Kubernetes security, advanced security, about mesh networking, about operators, and so on and so forth. So you can have a look at those. They go a little bit more into depth at what we'll be doing today. So it's really just an overview of those topics that we will have today. So if we just talk about the context, everybody's talking about disruption today. So the business landscape has radically changed in how we communicate and interact with service providers. Be it I want to be able in the evening sitting in my sofa to order something from Amazon, or I want to be able to do my e-banking on my phone while waiting somewhere at the post office or something. The ones very famously like Kodak, they didn't get it, or they didn't see it coming, so they have been disrupted. So basically, I don't know what Kodak is doing today, but I think they're selling socks or something. No, I'm joking, but they really went out of business and trying to come back now. But there's a lot of examples of very well-known brands who didn't see it coming, this change in how we interact, and some of them went out of business. Just think about the new players like Netflix. I mean, cinemas are dying, Netflix is thriving. The same thing between taxis and Uber and so on and so forth. So what we need to be able to address those challenges is to do digital transformation. So to go from the old way of operating to new, more modern online mobile way of doing things. And most customers I'm working with, they are pretty much to the left. So that means that they are just starting with this transformation, and they start adding new features in a, what we call cloud native way. So in a modern way, small pieces. We'll talk about that in a second. But usually they just add new features in this new cloud native way. So they don't touch the core systems that they already have. They might be doing what we call lift and shift. So taking VMs, for example, that are running on premise and put them into the cloud to have the flexibility with cost and moving stuff around off the cloud. But that's just the start. So that's not the real transformation in itself. And lift and shift, I just discussed that yesterday with a customer. It's not as easy as lift and shift. Usually it's lift, adopt, and do some stuff, and then shift it over. So it's not that easy. But what we're seeing is that it will take roughly 10 to 15 years for most of our customers to get to the right, where we really have microservices implementation and a really modern cloud native approach to development and running our IT systems. And as you can see, there's still some dark blue legacy hosted stuff. There will be systems that cannot be transformed, technically speaking, or that don't make sense to be transformed because the business value isn't just worth it, so that the business value is lower than what it would cost to transform them. So with this background, let's dive into microservices and containers, which are a very important part of this digital transformation. Another one would be DevOps. Cannot be talking about that today, because if I start talking about DevOps, we will still be here at 6 p.m. So let's just start about the foundation for those transformations, which is microservices, containers, and Kubernetes. So what are microservices? Basically, microservices is taking your big monolithic application that you have, where you have everything just in one big package, and slice it up in small pieces that you can handle independently. So you can deploy them independently and you can operate them independently. Let's talk about that. So an example for a monolithic architecture where you have the UI, the business logic, the data access logic, and everything just in one big package with a big hunking DB underneath, like Oracle or Microsoft SQL or whatever. That's the classic way of doing. So the idea is splitting that up in small services that just have one purpose, for example, customer management or credit card management, or for flight reservations, for example, the seat availability, and so on and so forth. And each one of those, and I'll be talking to that in a second, has its own data schema. So that's very important. We'll be talking about that a little bit later. So what are the key tenets of microservices? So we break monolith into small services. We've seen that each service has its own process, one service per container. I talk about that in detail afterwards when we talk about containers. A service is optimized for a single function. As I said, for example, a credit card management, seat management, whatever. Single responsibility, okay? That's very important. If you do it bigger, you will not be talking about microservices. Communication between microservices in this big mesh afterwards that we have is done usually either through REST APIs, which is pretty standard, or message brokers if we need asynchronous communication between the different elements, and we need to be sure that messages are delivered, and so on and so forth. What's cool about that is that we can have per service continuous delivery. So if we're talking about DevOps, continuous delivery, and so on and so forth, each service can be developed and tended to by a small team. That's what basically DevOps is all about. They can deliver at the speed they want, and they can have their own CI/CD, so continuous delivery pipeline. So some might use some more classical stuff like Jenkins, for example. Others who are using really cloud native container-based stuff might use stuff like Tekton or other evolving technologies. And very important, we have this per service high availability. So we can cluster those microservices, we can scale them up, scale them down independently. If we talk about the monolith, it's pretty darn complicated to scale the whole thing, because you cannot scale the whole monolith in itself. So if we have per service scaling that you can apply, you can, for example, just start scaling, I don't know, a certain service that handles some business topics that are seeing increased traffic, for example, before Christmas for the Christmas sales and stuff like that. So it's very handy. So those are what we call the key tenets of microservices. Now, each component, as I said, is developed independently, has limited and explicit dependencies on other services. So that's very important. Here we're talking about APIs. Each microservice should have very specific and stable APIs so that you don't introduce additional dependencies. So that means that you can change the behavior or the code or whatever of the microservice, you can have it evolve. As long as the API stays stable, you won't affect the other parts of the system that are consuming this microservice. So usually they're developed by a single small team. Obviously, we talk about these 2 pizza teams and the ones that have already followed the other courses. Think about American pizzas, not European ones. So the teams can be a little bit bigger than we're used to, but usually it's just a team that can be fed by 2 big honking American pizzas. Okay, so small teams meaning. The timetable, so one microservice, one team can release, I don't know, once every 2 weeks, another one can release each day, for example. We have this, we introduced this independence between those microservices from a timetable perspective as well. So they scale independently, I already said that, and they fail independently, very important, meaning that if a microservice fails, that could mean that, for example, you just cannot use your voucher codes on a website where you can order some stuff. It's not the whole website that goes down, but it's just little parts of functionality. If it's very central functionality, obviously it will have a pretty big impact, but the idea is to keep as much running as possible. Another one is that you can use the technologies and the languages and the databases that you want. This one is a two-sided sword, and it's a little bit walking the fine line, because if you let each and every team decide what technologies they will be using, you will find yourself with some sort of anarchy, with some Node.js, some Java, some .NET, some Erlang, whatever. So usually it's a good idea to have some guidance here, but to be pretty open, but have some guidance so that it doesn't go completely overboard, especially if you want to have people afterwards being able to change from one team to another one. It might be important to standardize some. And where it gets really important is for databases, for the licensing questions. You cannot just use a database here, another one there, and so on and so forth. Try to standardize on some databases, SQL or non-SQL databases. You can offer 2, 3, 4 choices, but then you can master your cost, your license cost for those databases and other stuff that might depend on it. Okay, so everybody loves containers, obviously. Why is that? Because it's a standard way to package up your applications. That's one thing, but also the dependencies. So they can be moved between environments, for example, from dev to test to prod, or from my local Mac where I'm doing some container development up to a huge cluster of Red Hat Enterprise Linux, for example. And we have this independence between all those different systems where we can deploy our containers. And that eliminates at the same time this works on my machine syndrome. I mean, you probably know that where you try to put something into production and it doesn't work, and the developer says, yeah, well, it worked on my machine. Yeah, well, but there's some DLLs missing on Windows, or there are some libraries missing on Linux, whatever. So you get completely rid of those dependencies. Everything's bundled in one big container. That's where the name comes from. So it's packaged. And you isolate the difference between applications and the underlying OSs and hardware and whatever. So you can vastly standardize here. So that's probably the most important slide of the whole course. If you've understood that, you've understood everything basically on containers. So if we look at the physical container, what the development is interested in is what goes inside the container. So it's all about the code, the libraries, packages, apps, some data, and so on and so forth. So we put that into the container. And containers are standardized from size and whatever, so that you can stack them and put them somewhere. So from a development perspective, all the Linux servers where the whole thing can run afterwards look the same. They don't need to care about where this thing will be running, be it on Red Hat, be it on Ubuntu, be it on Mac OS, be it on Windows, doesn't matter. So they just care what goes into there. The operations guys, on the other hand, are worried what's outside the container. So how do I do my logging, the remote access, monitoring, and so on and so forth. So they care about starting a container, stopping a container, migrating, and so on and so forth. So development puts their stuff, their code, their libraries into it, close the door, it's sealed, and operation takes over and can deploy the whole thing. And that's really important for modern CI/CD or DevOps processes, because it creates clear ownership of the boundaries between dev and IT ops. Very important thing. So containers are not new. I mean, people think that Docker, when it came up, was what they invented containers. That's not the case, because the concepts that containers are based on, they've been in existence since '79 with change root. Then came C groups, Linux containers, and so on and so forth. All those are concepts that allow us to run a process on a host system in a completely isolated way. And that's basically what a container is. Container is just a process that runs in complete isolation on a host system. Okay. Now Linux containers was pretty nifty, but it was still pretty complex to handle it and to work with it. So up came Docker in 2012. So they developed a solution around that was pretty easy to use. So you just had one command line and you could create containers, you could run containers, delete containers, and store containers and whatever. So that's where it really took off. But and then in 2014, roughly, came Kubernetes. And we'll be talking about what Kubernetes exactly is in half an hour or so. So that was coming two years later. And then to 2015 came the Cloud Native Computing Foundation, where Kubernetes and most of those projects are living under now. So it's a group that supervises basically a little bit what happens in the open source space. Then came Containerd. Those are the runtimes, CRI-O from Red Hat. All those are runtimes that help us run containers. I'm not saying Docker containers, really containers on a host system. And we'll be talking a little bit about that in a second as well. And I don't want to go too much into that. In 2020, Kubernetes announced that they won't support Docker containers anymore, which in itself is not really a problem, because containers are standardized. It's a standardized format called OCI. And you can basically create containers with Docker or with the CRI-O tools or whatever and have them run. So it's not that a biggie. But Docker had it coming, but I won't go down this rabbit hole, otherwise we will never fit in 1 hour. But just know that as of the latest Kubernetes release, Docker has been officially deprecated, not taken out yet, but it has been deprecated, and this Docker support will disappear in the future. So we'll either use Containerd or CRI-O as the runtime and not Docker anymore. Okay. So what's the interesting thing about containers? If we do a little comparison between VMs and containers, when you take your VMs, you have the hypervisor that's running on your bare metal, on your infrastructure, and each VM has a guest OS that's running. So it can be Ubuntu, can be Windows, can be Red Hat, Enterprise Linux, whatever. And on top of that, after you have your libraries, your dependencies, and the application that runs on top. So we have pretty good isolation because the VMs run each one separately, but we have to install each time a complete OS which has a pretty high overhead, and compute memory is pretty static. So if you want to increase memory, usually you have to shut down the VM and modify that and restart it and so on and so forth. On the other hand, as I said, a container basically is just a process, an application that runs on the operating system directly, so on the kernel. That's what we call the shared kernel between those processes. So if you look from the host machine, you will see all those container processes running. So from the host machine, you have an overview, and you can get the list of all the processes that are running. But from the process itself, you cannot see the other ones. So it feels pretty alone up there, because it cannot see anything else. And that's those C groups and change root and so on and so forth that I talked about, that are part of the Linux kernels today, that give us the possibility to do that. So those container, basically an application in this case, is just a process running on the host system. So you don't have all this guest OS stuff that you have to handle and install and update and whatever. Okay. And on top of that, computing memory is dynamic, because it's shared across all the processes that are running. And you can assign resources. You can say, okay, this container can use 1 gig of memory and two CPUs, for example. And you can adapt that, you can burst that without restarting the whole thing. So that's pretty flexible. Now, from the efficiency and the resource utilization point of view, if you think of VMs as big balls, when you put them in a recipient, you can put in, let's say, four VMs, and the fifth one would be too big, so you cannot do that. On the other hand, containers are really small processes that are running, so you can fit much more of those into the same volume, thus having a much higher resource utilization than you would have with classical VMs. So usually we go from VMs where around 50-60% to something like that, sometimes a bit more, sometimes a bit less, to up to 85-90% for containers. So it can also be a cost and an efficiency topic here to be using containers versus VMs. So just to wrap it up, advantages of containers. So they're portable, as we said. You put your stuff into the container, close the door, and you can run it, be it on a Mac, on Windows, on Linux, doesn't matter. They're pretty easy to manage, because you can build it. You can store it in a registry, as we call it, and I talk about that in a second. They provide just enough isolation. Obviously, isolation of containers is not as good as isolation when you're using classical VMs, because you don't have the whole OS layer that provides isolation. But up until now, there's very few problems that have been known, or vulnerabilities that would have made or that would have posed some security problems. If you want to know more about that, because you have to do it right, otherwise isolation is not here. Have a look at the videos that we recorded in May, June. We have 2 half-day sessions on container and Kubernetes security specifically here. They're more efficient, that we've seen already, and the most important thing is immutability. Because once you build your container, you put in your app in a certain version with certain sources, you put in your libraries in a certain version, you close the door, you seal it. So this container is, if you want, stuck in time and won't be changed. So you can be sure that what you created in dev, what you tested in the test environment, is exactly the same thing that will be deployed into production. That's very important. Okay, so from here afterwards, let's talk about the components, in this case of Docker, but it's basically the same for the other solutions as well. So what is a container? A container is what we call the smallest compute unit. So it's a running process of what you build. Now, a container is built out of what we call an image, and that's where it can be a little bit confusing, because what you build is an image. So an image is a little bit like a snapshot of a VM, and then you can create one or more VMs out of a snapshot, or in this case, you can create one or more containers out of an image. So what you're building from the container abstraction is an image. So the image is like the patron, is like the snapshot of that's not running, And then you can take the image and say, okay, I want to instantiate, if you like, this image, and that will result in a running container. Okay. Then the images are being stored in what we call an image registry. So there are different ones. There's hub.docker.com, for example. There is Quay.io from Red Hat, and so on and so forth. You can get your private registries. Obviously, if you want to create some business critical images that may contain some sensitive stuff, you don't want to push them into publicly available repositories or registries. So you can have your on-prem private registries as well. Okay, so you can either have private or public registries to store your images, and from there afterwards you can create your containers. And you can see each image has a tag, so you can put anything in there. It's not just v1.0 or something. You can put in Jim, Joe, whatever. But usually we put a version number or something in there. So like that, you know, when I create a container from web app 2.0, I know exactly what I'm implementing. One specific thing is the latest tag that's added automatically when you create a new image. So never ever use the latest tag to work with containers unless you're working in a dev environment or something, but never use that in test or production, because you never know which version of a container you are instantiating in the end. So if someone built a new image in the meantime, you will get this one instead of the one that you thought you would be testing. So it all starts with the Docker or with Docker build. So Docker build gets us input the code, or the deployables can be a WAR file, for example, for a web application, some config files, and what we call the Docker file. And the Docker file is basically the recipe that tells Docker or any other solution how to construct the image. So it's a text file, as you can see here, and then it goes through it. And very important, the first one usually is from. That means that we get an already existing image, and then we're building on that. So here, for example, I get an image for Tomcat 8 with JRE8 already pre-installed. So I'm basing myself on that. So Tomcat is already installed in this image, and I have a JRE8 in there. So you can get them either from Docker or from Quay or from your own registry, it doesn't matter. You could start from a completely empty image, so you don't have any binaries in there, you don't have any libraries in there, but usually we use what we call those base images that can be Ubuntu as well, or a CentOS or whatever, okay? So you take that, and then, well, maintainer is not that, it's just some meta information. Then you can run commands, for example, apt-get update or stuff like that. You can set environment variables. So here I would have the environment variable, my name, that's set to John Doe. You can add afterwards, and that's where it gets interesting, files from your drive, so from your local storage, into the container. So here, for example, for Tomcat, that would be the web.xml file it's basically the settings for Tomcat, and we copy that into the container to this user local Tomcat conf directory. And then we get the WAR file, which in this case would be the web application, and copy it into the web apps directory. So we are building, again, in this case, we're just putting all this stuff into the container, and then we say, okay, and now expose port 80. That would be the port from the standard port for Tomcat, the non-secure one. And then the last one is the command. This one is not run when you build the image, but when you start it. So when you create the container from the image, it will run Catalina sh run. So here you can decide what happens when you take your image and you create a running container out of it. Okay, so it goes through that recipe and creates the final image that is pushed into the registry. Now, running a container is just as simple as that. You just say Docker run. So you could say, for example, Docker run. You give it my image 1.0.0. You can give some variables. For example, here for the ports, It's always to the right is the internal port and to the left is the external port. Because, I mean, imagine you cannot run several containers, each and every one listening to the port 80, because we get conflicts here. So you map that to an external port where the container is reachable. So you would access the web application in this container through port 8080 that is routed to the port 80 inside the container. Okay. Then, well, what some flags, I won't go into detail yet, but just perhaps -D means daemon, so it runs in the background, so you won't get any output. It just runs until you stop it. -E is to pass on some variables. So here, for example, you could pass on a database URL or a database password and stuff like that you don't want to hard code, obviously, in your container. And for the second one, the -TI is terminal interactive. So I'm starting the image and I'm executing bin bash. So I start my container and I get a shell into the container directly. But we'll leave it at that. We cannot go much more in depth than that. But that's how you run containers, either as a daemon running in the background, that's what you usually do, or if you want to debug or get into the container, you can run it with this -TI with bin bash. And then the last part is how do I store the whole thing? So that happens with Docker push and Docker pulls. So as soon as I create an image with a Docker build, it will be stored locally on my machine. Now I want to publish that. Okay, so when I do Docker images, I see the images that I have locally on my machine. So what I would be doing afterwards, I can either tag it, for example, give it a new tag, and then push it into a registry. And from the registry, I can pull it out again. So the registry is like the phone book where I can publish my images in a certain version, okay? When you do a Docker run, let me just get back here. When you do a Docker run, usually you would do a Docker pull to get the image on your machine, and then you do a Docker run to run this image and create the container. But Docker run automatically does the pull. So I guess the last time I used pull was like 3 years ago. So when you do a Docker run and the image is not yet on your machine, it will first pull the image and then run the container out of it. Good. Any questions? So if you have questions, you can unmute yourself.
Actually, I would have to unmute them. It would be great if you could post them in the Q&A section.
Well, I don't have access to the Q&A sections while sharing. That's the thing. So
I can assist you over here.
No, I got it. I can show it overlay, but there's nothing in there for the time being, I guess. Okay. So if you have questions, you can post them in there, or I'll try to pause time to time. You just have to unmute yourself. Can they unmute themselves, Christiana?
They cannot unmute themselves. I would have to know whether they have a question or not to unmute them.
Okay, so if you have questions, post them in the Q&A, and either we will unmute you or we'll reply to the question. Okay, so I guess there's no questions so far. So let's go on. I just inserted a little bit of a let's get real part, because containers and microservices are super cool and they're modern and they're extremely sexy and whatever, and everyone wants to do containers. Now containers don't always make sense. Just keep that in mind. It's not just because it's a new technology and it's sexy and whatever that you should implement containers. Okay. Let's start with this statement. Containerizing your WAR file doesn't mean you're doing microservices. Because taking your web application, as we say here, your WAR file, for example, and putting that into a container is not really doing microservices. Why is that? Because we still have this dependency through the databases. So as I said, we have to have including databases, because if you have, let's say, 3 microservices that are accessing the same database, if you have a schema change in the database, you again have impact on all those microservices using this central database. So you keep a point of dependency in the form of a central database. So usually you should split up this database, and that's where microservices get really hard. As I said, putting a war file and splitting it into a container, splitting up your UI and stuff like that, it's not that complicated. But taking your big hunking database schema and doing domain-driven analysis and understand which data is stored where and how you can cut that in pieces and get for each microservice the data that he needs, that's much more complicated, believe me. So if we have a look at the monolithic application that uses a big database, so that what's usually done or very often done, and I see that quite a lot at customers, is what I said. So they start creating microservices with their own REST API, but they're still using one central database. So as I said, that's not good practice. So what you should do is to have a database per microservice. So for example, one is for customer details, another one for customer accounts, another one for customer address, and so on and so forth. So if you have a very well done relational database schema, that should be pretty easy to do, because basically what you do is as soon as you start using foreign keys, for example, between tables, that means that there's probably a way to cut there and to take it apart. So the idea here is really to have, when I want to get customer details, for example, customer details goes into its own database and gets some basic information, and then customer details doesn't go directly into the other databases, but it goes out and through the REST API, calls customer address, gets the address back, then it gets the customer account, and then it gives the answer back. So this obviously, again, decouples those microservices completely one from each other, where we get the benefits of independent scalability and so on and so forth. On the other hand, you have to pay attention, because each REST API call can introduce some latency. So if you have a service A calling a service B, calling a service C, and so on and so forth, each time you introduce a certain latency. So try to not do very deep chaining. So try to keep the structure as flat as possible, but always go to the external route through the REST API, so that the central service calls other REST APIs, gets the stuff from there, and gives it back. Like that, you will ensure that we get this independency. Okay. Questions? Still no questions in Q&A, I guess, unless it's not refreshing. Okay.
There's one right now.
Yes, it just came up. If I intend to use containers, but I have to do some adaptation always, proxy environment, what is the best way to make my additions permanent? I'm not sure I understand the questions. Could you unmute, Rüdiger? Christiana?
Yes, I will do it for you. Just 1 second. There you go. You're now unmuted.
You can ask away.
You can hear me?
Yes, we can.
Hi. Now the question is that I'm always in doubt if I have a command line for starting my container, and I measured that I have a lot of things in this command line what I have always to repeat, and I'm thinking to make this one in a style of permanent to get my own style, where in example a proxy environment of my environment is just inside, and because I need it in likely every container, is that the best to put it in components or make my own variant of this container, or is it better to make a script what always is getting started with the container, or what would you recommend?
Okay. Well, you said compose. Compose would be a possibility now. What you have to keep in mind, and that's where we're going next here, is that you probably, hopefully, never run containers on their own just like that. So Docker run is good for debugging. It's good to see if the stuff works. but it's pretty complicated to manage all those containers, and that's where Kubernetes comes in. And I'll go a little bit more into detail. And proxying stuff and things like that usually are handled by Kubernetes afterwards, so you don't have to do much here. Okay, so if you really want to work with containers alone, then Compose would certainly be a good idea. So Compose file that would run a container with a proxy in it, and another one that runs your application container and pipes the traffic through from the proxy to your application container, stuff like that. We'd have to look in detail what you want to achieve, but that's a possibility. But Kubernetes can do that automatically. That's the cool thing.
Okay.
Okay. So what I suggest is that I go through the Kubernetes stuff. If you still have questions, we can take it afterwards. And it's already 44, so I have to speed up a little bit. Otherwise, we'll never finish at 3 o'clock. Okay. Okay, I guess you muted. Just in case, if you have questions or something, you will have my contact at the end of the presentation, so you will be able to contact me, drop me a mail or something. Okay, good. Now everybody loves containers. We've seen that. Now, but what happens when we go from this, when we have like 4 or 5 containers, to this, where we have 100, 200, 1,000, 1,500 containers? If you think Google every day starts and stops, I don't know, I don't remember exactly, but I think it's 150 million containers. Okay, so that's just not humanly possible to handle that manually. So a lot of my customers back 2 3 years back started, yeah, we're starting to play with Docker and containers and stuff. They had 5 6 containers. Went back 6 9 months later, say, oh, now we have like 50 containers. It's absolutely impossible to handle that manually. And that's where Kubernetes comes into play, because when you go from this to this, it gets hairy. And that's where we talk about pets versus cattle. So let me just elaborate on that for a second. So pets versus cattle comes from pets that are the VMs. So it's your little cute cat. If it dies, you're happy, you have a problem, your production environment goes down. On the other hand, we have the cattle, which would be the containers, the microservices. It's like having 1,000 chickens. If one chicken dies, you just buy a new one for 5. Not a big problem. So we have this duality. When you have VMs, you really have to tend to it, that it's never crashing, that it's running all the time, and so on and so forth. And on the other hand, we have those microservices that must be able to stop and restart without having any major impact, okay? So the whole monitoring paradigm is shifting as well, because when you're monitoring your environment, when a VM goes down, you want the red flag, and you want to know that, and you want to get a PagerDuty alert or whatever. When a container goes down, you don't want an alert, because if you get an alert each time a container goes down, in my demo environment, I have like 10, 15 containers going down each 5 minutes. That's absolutely normal. But what you want to know with containers is if the container restarts 20 times a minute, for example, then you probably have a problem. So we have this shift in paradigm in monitoring and how we handle the whole thing. And that's, as I said, where Kubernetes comes into play. So what's Kubernetes? Kubernetes is a declarative system. So we have imperative and declarative systems. So imperative systems is where the user says, okay, I want to go from here to there in my system state, and I know exactly which steps I have to execute to go there, and we execute that. So that's the Jenkins and the Ansibles and Chefs and Puppets of this world. Then we have the declarative system, where you say, okay, that's the state that I want at the end. And then the system automatically knows how to get there and does that. And that's what Kubernetes is. So we're talking here about the desired state. So I'm telling the system, I want 2 instances, 2 containers of my app 1, 3 of my app 2. My network should be like that, and my storage should be like that. And then it goes out and does that automatically. So it starts the containers, or pods as we call them as well, does the port and service declarations, does the volumes on NFS or whatever system you have. And all of that is coded in YAML or JSON in a text file. Okay, so you say, I want this to be running, and the system takes care of getting there. And what's more, and let's talk rapidly about the architecture of the whole thing, it can do that automatically and always enforce that. So we have what we call the master nodes. So those are the orchestrators, if you like, the conductors. So usually we have 3 or more for failover. So if one goes down, another one can take over. So we have 3, 5, 7, and so on and so forth. And that's where I store my desired state. So through the API, either through a UI or command line interface, I say, okay, that's the text file, the YAML file. That's what I want. And now do that. And what it will be doing, it will deploy that to what we call the worker nodes. So the worker nodes are the ones who are doing the heavy lifting, where those container runtimes are running in the end. So that's where the containers are running. So it says, okay, I have one instance of app 1 on this worker node, and so on and so forth. Now let's imagine a worker node goes down. So it will say, okay, I wanted 2 instances of app 1. I just have 1 left, so I'm missing 1. So it goes and looks for a worker node that has resources and redeploys a container on this worker node. Okay, so it does that automatically. So it's extremely robust. You can unplug a whole worker node, and it just reshuffles the containers, the pods running on other worker nodes that are available. So it does that automatically. Desired state. And there's an endless loop that just looks at it. What do I have? What do I want? And tries to achieve this final declarative state. Now for the terminology rapidly, a pod is the smallest deployment unit in Kubernetes. So a pod usually has 1 or more containers in there. Normally just 1 container. I cannot go. We just have 10 minutes. I cannot go into detail why that is. You have that in the videos if you want to see it. But usually it's 1 pod, 1 container. It encapsulates the container running. Then usually you don't deploy pods themselves. What you do usually is a deployment. So you say, I want to deploy a container. I want to have 3 instances of that, and so on and so forth. And what that does, the deployment creates what we call the replication set. Replication set is this endless loop that verifies if 3 pods in this case would be running. Okay, so in Kubernetes we often have this 3-layer, this holy trinity, where you have 3 levels of abstraction. It happens with storage. It happens with a lot of stuff. So that's what you're doing normally. So you create the deployment that will create the replication set that's responsible for checking if everything is running, and that creates the pods that should be running with the containers within them. And the service, that's the next one. That's just that's here to expose pods or containers to either to the cluster itself or to the outside world. So usually, what you need, the minimal deployment would be a deployment and a service that says how you can access this deployment. Very rapidly, a very high level view of Kubernetes. So Kubernetes has what we call common interfaces. So a common storage interface, common network interface, and a common runtime interface based on this OCI standard. So for the runtime, basically I can plug underneath whatever I like. It can be Docker, can be Cryo, can be Containerd, and so on and so forth. So as long as you write your YAML files for Kubernetes, you don't have to care what runtime is running. So we can replace Docker with Cryo without any big problems. The same goes for storage. So your Kubernetes deployment can say, okay, I need 20 gigs of SSD object storage, for example. And the common storage interface goes out and sees what storage solutions have been attached to the Kubernetes cluster. And it can be NFS or RUKSEF or GlusterFS or the VMware stuff. And it just takes the one that makes sense. And it's completely transparent to you what is used. And the same for the network interface. You can use Open vSwitch, you can use Calico. There's a lot of different plugins that you can use for common network interface. You don't have to take care of that. So that's a cool thing. And that's why I think that Kubernetes will be around for quite some time, because we have complete abstraction from the underlying implementation, the physical implementation that we have underneath, and that's completely exchangeable. So that's pretty nifty. Now the cluster, I'll be very fast on this one. So we have the master nodes with the API server. API server stores the desired state in this distributed storage. That's based on etcd. That's an open source project. Then we have controller and scheduler who are responsible for checking the desired state with the actual state, and then they tell the worker node through the kubelet. That's just a little piece of software that's running on each worker node to deploy the pods, or in the end the containers. And on each worker node we have kube proxies. So those are proxies that are running to connect the outside world, the internets, to the workloads that are running on those worker nodes. So that's basically it. And I really have to speed up. A pod, basically, you just create your YAML file. You say, you give it a name. You say, I want to create a pod. You give it the image, and you say what ports you want to expose. And that's it. And it would create the whole thing. I won't go into that. Then the services. That's an important thing that we have to treat. So a pod itself, the container, as we've seen in the example, has the port 80 that's exposed. Now, if you want to expose that, for example, as port 8000 to the outside world, we do that with the service. So I say kind service, external port is 8000, the target port internal is 80, and then we attach it through what we call selectors to the pod. So this pod has a label, app nginx, and the service will find the pod to attach to through this selector. Once it's done, this service will be registered in the internal DNS, and another pod, for example, could refer to this pod through the service name, so nginx service. So it will automatically resolve, in this case, to 10.0.0.1. Because those IP addresses, when the pod or the container restarts, which can happen quite often, this IP address changes constantly. So you cannot call stuff internally through this local IP address. That doesn't work. So create the service, and then you can use just a simple DNS. Then for exposure, so cluster IP is the internal one. That's what we've seen. So if you do cluster IP, that's the standard default one. Your pod is just visible inside of the cluster and not from the outside. So you get some security baked in here, if you like. But if you want to have that externally used, we can use for development what we call node port. In this case, it creates a dynamic port from 30,000 to 33,000, I guess, if I remember well. And then you can access it from the outside world. So you can say my cluster IP colon 31,250 or something, and then you can access that. But obviously you don't want to do that. You cannot have, I don't know, your banking application on creditsuisse.ch colon 31,000 something. That doesn't work. So that's where a load balancer comes in, where I can use an external load balancer that exists in your system to pipe the traffic through it. Again, we cannot go much more into detail. Again, I refer you to the videos. That we go over it. Just one important thing, a deployment. How does it look like? So I have a kind deployment. So that's the deployment part. Then we have this part here where I say spec replicas 2. That's the replica set, more or less. And then I have the pod part where I say containers name with the image and the container port. So it's not 100% accurate, but just that you can see complete deployment, which part is more or less creating which Kubernetes object. So this is creating the pod. This is the green one is creating the replica set, and the rest is creating the deployment itself. This three-level hierarchy. Good. Questions? Yes, there was a question in the chat. What are the microservices you mentioned have its own DB? Do you recommend containerized DB or not? Oh, hell. Going down the rabbit hole. It depends on the DB. You can get Oracle databases fully containerized today. So you can deploy a containerized version of Oracle. Now, what you have to know, if you deploy a pod or a container, doesn't matter, of Oracle, if you write stuff in there, it's just in the container. When the container dies and restarts, this information is gone. So a pod should never store state when it's running. So we need external solutions for that. And as we've seen, Kubernetes through the common storage interface gives us this possibility. So I would start up an Oracle pod, an Oracle container within Kubernetes, and external storage through this CSI. So the data itself that goes into the database would be stored in an external storage provider. And if the pod goes down and comes up, it just hooks up to the storage again, because it will remember that automatically, and the data will be here. So that's very important to know. So basically what you're running in the container is the database engine itself, and not keeping the data. So you have the database engine, and the data is externally stored through the common storage interface, and it's just accessing the data. Now, it depends on what you're having. If we take an Oracle database with a lot of stored procedures and triggers and whatever, that might, let's put it that way, it's probably not a good idea to containerize that from a performance perspective. I think the good old databases like Oracle and probably also Microsoft SQL Server, they will mostly stay on-prem classic in a VM or something. Now, if you like, you can do a containerized Oracle database or a containerized Microsoft SQL database if you're small and just having the data that you have. But what we're using when we're really going into containerized databases is more like Postgres, for example, or MySQL or MariaDB, which is the fork of that for the SQL database. And for the non-SQL databases, you might be using stuff like MongoDB, or you might be using even stuff that goes further, like Kafka, for example. So those are more modern cloud-native databases, if you like. And then we have the more classical, older ones like Oracle and so on and so forth. So but the system is still the same. You say, what about MongoDB? It's always the same thing. If you start the MongoDB as a container, the data will still be stored or must be stored externally, because if you start the MongoDB without having external volume or storage, when it goes down, the data is gone. So system is always the same. It's just that the old school, if I may say, databases are not that optimized for containerized optimization. But we're getting there. I'm sure that Oracle has made a lot of progress. I couldn't tell you because I'm not working with Oracle. We're working with Postgres. We're working with MongoDB and stuff like that. But that's about it. And you have another question. How about app persistence? Well, app persistence is exactly that, because a database in the end, it's an application running. It's a database application, if you like. So app persistence is exactly the same. If an app has to write some stuff somewhere, if you just write it into the container or in the pod, and the pod restarts or is taken from one worker node and placed on another one, which happens pretty often, you lose your information. So what you do is you get the storage volume again through the common storage interface, and you map that in a certain place in your container. So you can say, for example, I want a volume of 20 gigs on NFS, and I mount that under /data/config, for example. Okay, and when you write inside the container into data/config, it's completely transparent. The container won't see that it's an external storage, but it will technically write de facto in the external storage. And if the container goes down, comes up again, maps that again into /data/config, and it will find the data that you have written in there. So that's how we handle persistence. Never ever persist stuff in your container/pods. You will lose that, okay? Eventually, because pods must be able to and will restart regularly, okay? So there are some mechanisms. I cannot go into detail with something that's called stateful set. That's similar to a deployment object, which keeps some how do you call that? Some coherence between restarts. So for example, the pod name will be the same, the IP address will be the same. You can do some stuff, but it doesn't store the data. It doesn't persist the data itself. Can we use caching? Yeah, obviously, but caching again has to have external data storage. So it can be an external caching solution where you write to. We're as I said, we're very often using Postgres to persist like more classical stuff, MongoDB for more unstructured data, and Kafka for very heavy load, heavy traffic stuff, where you really need the firepower to be able to ingest thousands of messages, for example, per second. So yes, obviously caching can be done externally. Okay, and we're on the top of the hour already through. So again, those are the sources and documentation. There's the complete documentation to do the hands-on labs as well in there. So if you like, you can follow the videos. The videos are here. The course videos, the online courses here. You can do the hands-on labs for Docker and for Kubernetes and for security and for service mesh and for whatever. So you can practice that if you like. And we will have, as I said, this Kubernetes Advanced Topics course that will be coming up. We'll announce it on the Slack channel for those who have already been in there, and through the Meetup platform. So keep an eye on the Meetup platform. You will see when we get to it.
Nick, I just got a private question whether you could share the presentation as well.
Yeah, the presentation will go here. Sorry, it will go here. GitHub, Nicholas here, Kubernetes Training Public, and I guess Christiana, you can post it into the Meetup afterwards. The link and the presentation.
Sure.
We will do that as up. Okay, cool.
Great.
That was really a very rapid overview. It was way too short, unfortunately. But yeah, I mean, if you would like to get the complete training, as I said, either watch it on YouTube if you're working somewhere for someone who would like to get a training internally for like 10, 15, 20 people. You can contact me or contact Christiana. We'll be glad to oblige if possible. And that's it from my side. Thank you very much for attending.
Thank you, everyone, and have a good weekend as well.
Yeah,
it's still a little bit early, but
yeah. Enjoy your weekend. Bye, guys.
Bye.